This is our final part of our mini-series on structural estimation workflow. And here we're going to be talking about validation and policy experiments, or counterfactual simulations. And just a little bit about validation. We covered it quite heavily in a couple of previous videos. So you can go back to those if you want to do a more systematic review. But just as a high-level remark, validation is at the heart of scientific progress. If we can't validate prior findings, then we really have no use for them. And the fields where validation is the fastest tend to be the fields that progress the most quickly. Economics is very difficult to validate because there are so many moving parts. It's very difficult to set up an experiment that holds all else equal for a lot of the phenomena that matter. So we can't have experiments where we're raising the Federal Reserve rate and seeing how that affects the banking sector and home construction and interstate migration and so forth. So a lot of these things we have to rely on the best models that we have available, and we may not be able to fully validate those models. Again, you can go back to the previous videos if you want to hear more about that particular topic. Let's now move on to policy experiments. Policy experiments is where we actually get to say something about the world based on all of the work we've done to develop and solve and learn more about and estimate our model and validate our model. And the policy experiments are the end goal, so we should have that end in mind when we're going through all the other steps so that we don't waste time working on some refinement of our model that has no bearing on the actual policy experiment that we want to run at the end of the day. So just to kind of review some ideas from a prior video, we have that structural estimation will give us the data generating process for our model. And once we know this data generating process, we can use it to run policy experiments by setting certain parameters equal to certain values or doing other things with the model to simulate data from it, and then look at, what's this policy that I've encoded through these certain set of parameter values, how is that going to affect some outcome that I care about? And the nice thing is that the policy that we run with the model may not be one that's actually ever been implemented in the real world. And so we can assess these proposed or hypothetical policies. And one thing I should emphasize here is that we're implicitly assuming that changing the values of the parameters of our model is not going to affect other parameters in our model. So we call this local policy invariance, or we just say that we're only making small changes to the world so that we're ruling out the Lucas critique, which says that if the government makes a policy change, then people will re-optimize to get around that policy change as much as possible. So we should just be clear that that's what's happening when we're doing these policy experiments. And then, assuming that all of that stuff holds, we can actually use our model to quantify not only what's happening to a hypothetical policy, what's the outcome going to be, but we can also quantify the exact mechanisms by which that policy is enacting that outcome. So let's kind of walk through how we might do this in Julia in, again, a very stylized example. So we've got our data frame, and we're just going to make a copy of it and call it data frame CFL for counterfactual. And then we can just adjust the EFC value. Let's just say we're going to run a policy experiment where everyone has less EFC. This is not a particularly compelling policy experiment, but we're just trying to illustrate how this works. So I have my baseline results, which is given my parameter alpha hat and the data that was actually used in estimation. What do I predict the base schooling probability to be? And then I can do the same thing with my counterfactual data, and then I can compare what happens. So in a prior video, we showed that there was a positive coefficient on EFC in the schooling equation. So we would expect that if we lowered EFC, then we would lower the share of people who finish college. And that's exactly what we see. It goes down by close to 1 percentage point. So again, this is super stylized model, so we're not going to read too much into this, but this is like an example of a very simple policy experiment that we could run. And as we close out this video, let's do a quick review of the pros and cons of going through this structural modeling workflow. So if you watch that video where Mike Keene is walking through all of the steps of the structural workflow, some of the things he says that are positives about structural modeling that I definitely agree with. I'm not sure if these are his exact words, but there's some combination of his ideas and my own feelings. So the main plus is that we can examine the effects of policies that have never been enacted or implemented. We can also learn more about economics by looking through the lens of a model. So sometimes, if we have a rich enough model, we might use it to uncover some previously underappreciated behavioral factors that might be affecting the particular setting that we're studying. We can also use these types of structural estimation methods to assess the performance of theoretical models and how well they can explain real-world data. And over time, with many such models in a particular subfield of economics, we can build towards a canonical model of behavior. So this can be useful, and this has been done, for example, in understanding the impacts of raising taxes on labor supply. So this is stuff that Michael Keene has worked on. Rush Chetty has some well-cited work about how to use sufficient statistics in these sorts of models. And then there's also a certain enjoyment that you could get from the rigor of these more complicated models that require more complicated econometrics. Some people might feel that doing regressions all day is a little bit boring, so let's spice it up with some nonlinear optimization. And then a final mark in favor of this structural estimation workflow, or the approach of using a structural model, is that observational data is a lot cheaper to collect than experimental data. And so if we're using these structural models, we can use them on observational data and still make scientific use of the data that's been collected. What are the downsides of structural modeling? This is more my ideas, I think. First, it can be really difficult just to develop a model that is both tractable and realistic and an extension of previous work. It can also be difficult to understand identification in these types of models because it's not a design-based identification like you would see in a natural experiment or a randomized experiment. Sometimes the more complicated econometrics are not very fun because they're too challenging. It can take a lot more time to program up and obtain the estimates that you're after. So if time is of the essence, then these structural methods might not be for you. And then, as you can see, I've taken time to go through these videos and walk through a very stylized model of schooling choice. And already it was starting to become pretty complicated. So that's the cons of structural estimation. And the idea is that now that you know what you're getting yourself into, you can make a more informed decision, which economists would predict would increase your welfare because you have more information to make the decision that best suits you. I hope you found this mini-series helpful. Definitely want to give a thanks to Michael Keene for producing his video, and hopefully I've added a little bit of value by walking through a more specific example. Thanks for watching.